We'll address in a minute what was happening when the rail was moving at that constant velocity on the incline. If the rail is moving at constant velocity along the floor, the only way that can happen, let's say again we have the 0.4 Newton frictional force. The only way we can keep the rail moving at a constant velocity along the floor is to exert a 0.4 Newton force in the opposite direction of the frictional force, exerting the force on the rail. Now, this force is exerted on the rail. Last time we saw a diagram like this, we were referring to the force exerted by the rail. If the rail is going to attain a constant velocity, it should have a zero net force. You should have enough force here to exactly counter but not exceed whatever force is resisting the motion. Okay, this is an illustration of Newton's second law. When the net force on an object is zero, then that object will have a constant velocity. That's essentially Newton's first law. He stated it when an object is in motion. It's going to continue in motion along a straight line at the same speed unless a force comes along to change either its direction or its speed, or possibly both, of course. Okay, the constant velocity acceleration means constant velocity motion means no acceleration. No acceleration means no net force. All the forces are in balance and they cancel each other out. Now, if we consider what's happening on the incline, let's zoom in on the incline. We made some measurements. That slope where the rail tends to go down the incline at a constant velocity is a slope where the hypotenuse is approximately 121 centimeters and the rise is 18.9 centimeters. That is a slope that's going to give us a constant velocity for the rail on the ramp. Now, how does that constant velocity come about? What forces are acting on the rail? Well, we think about it, we can name at least three forces. There's the weight of the rail, which we saw was about 2 newtons. And this weight is the force exerted on the rail by gravity, by the mutual attraction between the mass of the rail and the mass of the earth. The rail and the earth attract each other equally, with equal forces. The reason the rail seems to fall to the earth rather than the earth rush up and meet the rail is because that force has a lot more effect on the rail. The rail gets a lot more acceleration out of that force than the earth does. However, there is a mutual force. The earth does feel a force just as the rail does, assuming that the earth even notices. There is a force. Now, there's a frictional force, obviously, that's opposing the motion, so that frictional force acts in the direction up the plane. And then somehow the plane has to support this rail. Now, without going into the details of why and how, basic idea is that the plane can exert a force on any object resting on it that's perpendicular to itself. Now, this force does not include the force of friction. That's a surface-to-surface force. This normal force is a different kind of force. So we have a normal force, a frictional force, and the weight. And the question is, can these three forces be in equilibrium? Can the net total of those three forces possibly be zero? Is it possible to pull in this direction with one force, in this direction with another, and in this direction with another, and have those forces in balance? Well, intuitively, it seems certainly plausible that that could happen. After all, we have three different directions. These two forces are going to tend to straighten out and push in this direction. The friction could well negate that effect.